In Unit 5, we examined polynomial, rational, and piecewise functions. So in this first lesson, we're focused on polynomial functions. Reminder that a polynomial is defined as an expression which is composed of variables, constants, and exponents that are combined using mathematical operations such as addition, subtraction, multiplication, and division. No division operation by a variable, though. The two main features that we have to have for it to be a polynomial is that the exponents have to be whole numbers, 0, 1, 2, 3, 4, 5. Nothing negative, no fractions, no decimals in the exponents. The coefficients have to be real numbers, so we couldn't have our imaginary unit I as a coefficient for it to be a polynomial. Reminder that degree is the highest power on x, so it's the highest exponent. Coefficients are the numbers that sit in front of your x's. The x is the variable, and the constant term is the number that's just a number. It's not attached to an x. Shape and continuity. So they are smooth when we graph them. There's no corners, like an absolute value function would have. It's a continuous curve. The domain for all polynomials is negative infinity to infinity. We can use any kind of value for x and get an answer out. And again, remember, degree is the highest exponent on x when the function is written in standard form, or when the polynomial is written in standard form. So the degree tells us a lot about the shape of the graph. Even degree polynomials. So if the biggest power on x is an even number, the ends are even. They go the same way. They both point up if the leading coefficient is positive, or they both point down if the leading coefficient is negative. And so the limit on the left side and the right side will always be equal to one another because the two ends go the same way. They either both go up to infinity or they both go down to negative infinity. If, however, the highest exponent on x is an odd number, they're going to go different directions. Think of that d as different directions. One side would go up, the other side would go down. Which is which depends upon the leading coefficient. So if the leading coefficient is negative, left side's up, right side's down. It's falling from left to right. If the leading coefficient is positive, left side's down, right side's up. It's going up from left to right. The two limit statements will always be opposites of one another. So whatever the left side's doing, the right side would do the opposite. All right, so if we look at our first example here, so the degree is 5, which is an odd number. The leading coefficient is 4, which is positive. So odd positive looks something like this. It's going up from left to right. So our limiting statements, the limit as x goes to negative infinity of our function f of x, well, the left side of this graph will be headed down to negative infinity, whereas the right side of our graph, so the limit as x goes to infinity of the function, will be headed up to positive infinity. All right, on this next example, here our degree is 4, so this is a degree 4, which means it's even. Leading coefficient is negative 1, so it's even negative. So we know even functions, the ends are even, they're at the same spot. Negative means they're both going down. So both the left and right side of this graph would be headed down to negative infinity. So the limit as x goes to negative infinity, meaning the left side of the graph is headed down. The limit as x goes to positive infinity of our function is also negative infinity because the right side of the graph is also going down. So remember, there's always two limiting statements because we need to describe the left side of the graph and we need to describe the right side of the graph. All right, so the zeros are also known as the x-intercepts. So the x-intercepts of a function are also called zeros or roots. And so when we're solving a polynomial, that's what we're looking for. Where is it touching the x-axis? And when we're on the x-axis, the value of y is 0. That's why we call them the zeros. That's why they're the x-intercepts, because they're the points on the x-axis. So a polynomial of degree n has n complex zeros, real and non-real. Some of these zeros may be repeated. This is called the fundamental theorem of algebra. So the degree tells us the number of solutions. But again, we'd have to count double roots twice, triple roots 3 times, and so on. All right, so here's a double root. So remember, if you've got a factor that appears twice, it's squared. That's called a multiplicity of 2, or a double root. At a double root, you bounce, you hit the x-axis and rebound. It doesn't go through the x-axis and change signs. Whatever sign we were before touching the x-axis, we're the same. So if we had positive outputs before we touched the x-axis, we still have positive outputs afterward. Or if it were below, if we had negative outputs before it, we'd hit the x-axis and then we'd rebound back down into the negatives. If it's degree 3 or degree 1, any kind of odd multiplicity, it's going to pass through the x-axis. If it's multiplicity 1 single root, it's just going to go straight through like a line. Changes from positive outputs to negative outputs. If it's a triple root, it does it with a curve. It's got like a little hitch in it. It's a change in concavity. It's like a downward-facing parabola to an upward-facing parabola. But again, we pass through the x-axis. We change from negative outputs to positive outputs, or positive to negative at any of the odd degree multiplicities. In a polynomial, factors and zeros are related concepts. Factors are the expressions that, when multiplied together, result in the original polynomial, and zeros are the values of the variable that make the polynomial equal to 0. So the relationship between them is that if x minus a is a factor of the polynomial, then a is a 0 of that polynomial. So once we get it factored, we take each factor, set it equal to 0, and solve. So if I would take x minus 3, set it equal to 0, and solve for x, I use inverse operations to cancel out the 3 and move it to the other side, and that's why I see that my 0 is positive 3. Or for the next one, we'd have to subtract the 5 to move it over. So the 0 is negative 5. We'd subtract the 8, so we get negative 8. This is not factorable anymore, so it's what we call an irreducible quadratic. We got it down to a quadratic, but we can't factor it, so we'd have to use quadratic formula or completing the square to solve that. To find the zeros of a polynomial, you must first factor the polynomial. If a factor is an irreducible quadratic, you can solve the quadratic equation in any way you see fit, completing the square, square roots, or quadratic formula. So we're going to find the zeros and multiplicities of the following polynomial, and then we're going to describe the effect the multiplicity has on the graph. So if we want the zeros, it means that f of x is replaced with 0. We want an output of 0 for the function. First step in factoring is always GCF. So when I check all 3 terms, I see, oh, they all have an x. So we're going to factor out the x and bring it down to x squared plus x minus 2. And then I attempt to factor down that trinomial. So I know x times x will give me the x squared. So this times this has to give you your first term. This times this has to give us this last term. And then our outside product and our inside product have to combine for the middle term. Well, if I'm going to multiply to negative 2, I know I need 1 positive, 1 negative, which I can just go ahead and fill in since these were the same. And then 2 is prime. 2 and 1 are the only whole numbers that multiply to 2. I want to add to positive 1 here in the middle, so I wanted the bigger number positive. So if I check my factoring, x times x, x squared, negative 1x plus 2x gives us positive 1x, and then the negative 2. Once you have a completely factored zero product property, set each one of those factors equal to 0 individually and solve. So the first one's done. We have x equals 0. Here we've got to subtract the 2 and see that x equals negative 2. Here we're going to add the 1 and see that x equals positive 1. So our smallest 0 is negative 2. It has a multiplicity of 1 because that factor only occurred once. So it's a single root. Next is 0. That's also a multiplicity of 1 and a single root. None of our factors appeared twice, so these are all single roots with a multiplicity of 1. And so they are going to pass through the x-axis since they are an odd degree root. So So we're going to pass through the axis, meaning we change signs from negative outputs to positive outputs or positive outputs to negative outputs. All right, so again, we start by always replacing the y or the f of x or h of x or whatever it is with 0. This has a leading coefficient of -3, but we can start by just dividing each side by that -3 to cancel it out. If it's just a number, that's just a leading coefficient. It's not a polynomial factor. It doesn't have an x. All right, then we're ready for zero product property, so we can set each of those factors individually equal to 0 and solve. So we're going to get x equals 2, and then we get x equals -1/2. So our first 0 is -1/2. Its multiplicity was 5. So because that's odd, it's going to pass through the x-axis. The signs would change from positive to negative or negative to positive for the outputs. The other 0 is 2. This one was a triple root. Multiplicity of 3. So also it will pass through any odd degree or any odd multiplicity means we pass through, it changes signs. And again, we refer to this multiplicity of 3 as a triple root. All right, so what if we want to graph these polynomials? Well, first we start with those zeros. So replace f of x with 0. And then zero product property, set each of those polynomial factors equal to 0. And solve. So we've got 0, 0 for our first one. Here we'll subtract 2. And see that's -2, 0 for the x-intercept. Here we'll add the 4 over. And see that 4, 0 is our x-intercept. So we're at 0, 0, 4, 0, -2, 0. Next, we can use the fact that these are all single roots, since they all have multiplicity 1. And a sign chart to help us to understand how this is going to look. So on our sign chart, we put our zeros, so -2, 0, 4 has to be smallest to largest. We know if we would multiply this out, we would get in standard form. So if we multiply these two together, we're going to get x squared plus some other terms times another x is going to give us x cubed. Because we're just worried about that highest degree term. There'd be a bunch of other stuff, but this highest degree term is what we need because it tells us it's degree 3. So it's odd. Leading coefficient, there's not a number written there, so it's a 1. So it's odd positive. So odd positive, we know, goes up from left to right. Starts down, ends up. So we'll mark off the left side's down, the right side is up. And then because they're all single roots, they all pass through the x-axis and change signs. So because -2 is a single root and it was negative before it, it's going to be positive after because we're going to travel straight through. Same thing's going to happen at 0. We're going to go through the x-axis and change from positive to negative. And then same thing at 4, change from positive or from negative back to positive. Now the thing that's going to be a little different about doing this here in pre-calculus is we're going to add in some additional points just to help us get a little bit of a more accurate graph. In Algebra 2, we just filled in that sign chart and then did a quick sketch of the graph. Now we're going to try and find some values in each of those intervals in order to help us have a little more accuracy in terms of the highs and lows of this. So our first 0 is at -2. I'm interested to know what goes on in between. So like at -1, how high or low are we going here? So I'm going to go ahead and take -1, plug it into my equation. So -1 take away 4 will give me -5. So I'd have -5. This would be +1, and this would be -1. So -1 times 1 times -5 will give me +5. So it's going to go up to 5. And then let me see what's going on between these 2 points as well. So let's fill in 1, 2, and 3 and see what kind of values we're getting in there. So again, I'm just plugging into this equation. So 1 minus 4 would be negative 3, 1 plus 2 is positive 3, and this would be 1. So 1 times 3 is 3, times negative 3 gives me negative 9. If we plug in 2, this would be 4, so 2 times 4 gives us 8. This would be negative 2, so 8 times negative 2 gives me negative 16. If we plug in 3, 3 times 5 gives me 15, times negative 1 gives me negative 15. All right, so I'm going to count by 2s to try and make this fit. So I'm going to, on the y-axis, so negative 2, negative 4, negative 6. Okay, so at negative 1, we go up to 5. Positive 1, we're down at negative 9. And then all the way down to the negative 16. And then up to negative 15, headed up to that 0. So we know we start down, coming up here, down through these points, and then we end up. So there's our polynomial, our degree 3 positive or positively oriented polynomial. All right, so same thing, new problem. So replace f of x with 0. It is already factored for us, so we're ready for zero product property. So negative x equals 0, x minus 1 equals 0, x plus 2 equals 0. So we're going to get 0, 0. One, 0. And negative 2, 0. But we also need to think about multiplicities here. So we have degree 3, or multiplicity 3. So this is a triple root. That's a multiplicity of 3. This one was a double root. This has a multiplicity of 2. So at a double root, we're going to bounce. We're not going to pass through the x-axis and change signs. Whatever the outputs were before it, if they were positive before it, they're going to be positive after it. If they were negative before it, they'll be negative after it. At the triple root, it's going to pass through, and same at 0, which is a single root. For those two, it's going to pass through and change signs. So if I do my quick sign chart, and again, if we think about multiplying this out to put it into standard form, we've got negative 1 for the leading coefficient, and we're going to get x to the 6th power. Because we've got x squared from here times x cubed gives us x to the 5th, times another x, x to the 6th power. So this is degree 6, which is even. Leading coefficient is negative 1, so it's even negative. And we know even negative, they're both down. So we can instantly mark off that the outputs will be negative below the x-axis on the left and the right ends. And since negative 2 is a double root, it won't change signs. It was negative before, it'll stay negative after. 0 is a single root, so it's going to travel through and the x-axis and change from negative outputs to positive outputs. 1's your triple root, so that's why we see it changing from positive to negative, traveling through the x-axis there as well. Let's go ahead and find some other values, some other points, though, to help us get a little bit of a more accurate sketch of this. So I'm interested in what's going on in between each of those zeros. So I'm going to plug in negative 1. So negative 1 would be positive 1. Negative 1, take away 1 more is negative 2. Cubed would be negative 8. So positive 1 times 8, negative 8 gives us negative 8. Over here, this would just be 1. So we're just going to Negative 8 times 1 will give us negative 8. And then between 0 and 1, I'm going to plug in a half. So we'll have negative 1/2. This would be negative 1/2 cubed, which would be negative 1/8. So negative 1/2 times negative 1/8 gives us positive 1/16. Here we'd have 3/2 squared is 9/4. So we were at, we had negative 1/2 times negative 1/8, and so that was positive 1/16 times the 9/4. So we're getting a small decimal there. Oh, positive 1/2, that's what, sorry, I knew I was doing something wrong. I was trying to figure out. Let me write it down. Let's not do all of this in our head. So f of 1/2. So you'll have negative 1/2, positive 1/2 minus 1 cubed, and then 1/2 plus 2 squared. I was messing up that last one is what I was messing up. Because 1/2 plus 2 wouldn't be 3/2, it'd be 5/2. I was thinking negative 1/2 in my head. Okay, so negative 1/2 cubed will be negative 1/8, because 2 times 2 times 2 is 8. Over here, we're going to get 25/4. And so if we multiply that together, 2 negatives cancel. In the top, we're getting 25. In the bottom, 2 times 8 is 16, times 4 is 64. So a small positive decimal there. So most of our, for the most part, we are down under the x-axis for this one. Oops. So we need to drop down to negative 8. Okay, so I counted by ones. I just labeled every other one just for space and to make it a little more neat and organized. So we know we start down in the negatives. At negative 1, we're down at negative 8 because we've got the double root at negative 2, so it doesn't pass through. It's going to touch and rebound, stay in the negatives. And then in between the two, barely get above. So we're here. So we're going to start down the negatives, touch, rebound, pass through, barely go above, and then back down. But at 1, it needs to be a triple root. So let's try that part again. Start at the bottom, hit and rebound, bounce for that double root, comes down here, goes straight through. And then we've got the triple root there at the 1. So it doesn't go straight through. It's got like a little hitch to it when it goes through. All right, so that's how we create the graphs of these polynomials. Still sketches, but just slightly more accurate than we did in Algebra 2. What if we are given a graph, we want to write the equation? Well, first thing we want to look at is degree. Left side's up, right side's down, so right away I know it's an odd degree, because the ends go in 2 different directions. I also see that it starts up and ends down, so it's going down from left to right, which means the leading coefficient is negative. We're not going to get specific about the leading coefficient. We're not going to actually solve for it. So we're just going to put a negative out front to acknowledge that it's a negative value. Then I need to identify my zeros. So I see that it touches here at negative 2. So the factor would be x plus 2 when we move it all onto one side. And also we should acknowledge that's a double root. It's multiplicity 2. It's bouncing there. So that factor would have to be squared. Then we see it touching the x-axis here at 3. So then the factor must have been x minus 3. And we see that hitch as we go through, so we know that's a triple root, multiplicity of 3 there. So we'd have to have x minus 3 quantity cubed. So it's negatively oriented, x plus 2 squared times x minus 3 cubed. So if we check, 3 and 2 gives us 5, which matches that odd degree. We've got the negative out front, and those are the only 2 places where it's touching the x-axis, so those are the only 2 zeros. All right, number 8. This time I know it's an even degree because the ends are even. They're both going up. And since they're both up, I know it's positive. So even degree leading coefficient equals a positive. So we'll say f of x equals some positive value. Here I see my first x-intercept at -5. So if x equals -5 is the 0, x plus 5 is the factor, and it's just a single root because it's just traveling straight through. Here at 0, 0, we're touching, and it's a double root, so I'm going to need x to be squared. Slide this over a little. We like the monomial factors to be in the front, just so they don't get lost in the mix. And then we've got another one here at 4. And again, it's traveling straight through, so it's a single root, and the factor must have been x minus 4. So write a possible equation. That's a possible equation. F of x equals some positive leading coefficient times x squared times x plus 5 times x minus 4. So there's your recap of polynomials.